let's go ahead and get started with all that. So we're talking about IoT, and a lot of our time was spent discussing more of sort of a terminology or classification aspect of it, really trying to understand the answer to the question of what is Internet of Things. And we got there. It took a few iterations, and I think where we really got to was this understanding that um, the things are smart devices. So networked embedded systems or microcomputers, low powered computers that still have network functionality that are controlling something physical that we are interested in. And why it's then also referred to as sort of the Internet of Things is meant to kind of reflect the scale of these devices that we're talking about, as we saw some of the numbers, millions to billions of these devices. It is meant to be sort of compared to the Internet of Computers, the regular capital I Internet, and now there's also, in addition, and in a complementary way, this Internet of these other type of devices, these smart devices that we care about. That's really all the term means, and so you can use the term like smart device and resulting smart house, smart car, smart cities, somewhat interchangeably. We kind of know what they look like, and we talked a little bit about why we care, right? Why do we care about this separate from just computer and network security in general? And the first reason was exactly that, was just the scale, the ubiquity of these devices. When you have a billion of something, that is a separate concern than when you have a few hundred of something or a few thousand of something. That quantity is itself an important characteristic in and of itself. The other thing we talked about in kind of a hand wavy way on Tuesday was, well, these are by design kind of low power, low resource, low computational devices that are the quote unquote smart devices. And that has certain implications for the kind of protective and monitoring mechanisms one can deploy on the device itself. Some of the things we talk about really only make sense in sort of cloud scale, server scale, workstation, laptop scale environments. And some of those assumptions we make about what we can run on those computers doesn't hold as well when we talk about these relatively low power, low performance kind of processors that we would be running on. So there's a lot of these things. They're low power. That has implication as well. And then while the actual underlying economic or financial reasons aren't necessarily all that clear, there's just a general set of incentives that result in these being smart devices for which security is effectively something of an afterthought. At least historically, that has been the case. And so what we find with IoT security is the vulnerabilities are not new. The classes of vulnerabilities or the weaknesses that are being exploited are not in and of themselves new, but what is new is this whole new target, this whole new class of devices for which we're having to kind of relearn things as a security community we had already learned about in the past. And there's financial, there's economic reasons why that's the case. There's just severe price pressure on these devices. There's also this thought that it's coming more from a sort of a manufacturing base than maybe a software and computer science base of people who are developing these things. But the resulting devices are, in many cases, quite insecure. And so where we left off on Tuesday was talking about municipal IoT, or sort of quote unquote smart cities. And that's directly related to smart cars as well, just to give another classification of these potential smart devices or IoT devices. The acronym you will see in some context beyond just smart car is vehicle to everything, or V2X, or you'll see V2X. It's kind of a not super meaningful umbrella term that just refers to any sort of wireless communication between a vehicle, a car, and anything that is around it. So the X stands for like asterisk. V to everything is what that X is standing for in this context. And then you have the more specific terminology referring to what is the vehicle communicating with around it. Usually, again, via some Wi-Fi, oftentimes 802.11p Wi-Fi between vehicles to other vehicles, that's V2V, vehicles to some intelligent transportation system or infrastructure, but V2I. Then you also have this at least potential capability for vehicle to pedestrians, and that's meant to be bidirectional communication. And then of all these kind of acronyms here, vehicle to device is the one that's actually kind of taken off in practice. So vehicle, meaning your car, communicating with your device, presumably your cell phone, is something that's in common practice. Does anyone use vehicle to device today and just common in your own person? What do you use? Use Bluetooth? That counts. Oftentimes this is referring to Wi-Fi and more than just like audio or call, but that's a type of V2D. It falls under that umbrella. There's two major phone manufacturers, operating system manufacturers that implement V2D. Apple CarPlay is the big one. The other one is, anyone know? Say it again? And Android Auto is the other one. And that in terms of modern use today, that is of all of these, that's kind of the most common vehicle to device communication that we have here. And anyone who does use it, it can be quite nice. And it's possible. I mean, it's not that clear where what the future holds for large scale rollout of these other capabilities. It's possible that vehicle to device with then some centralized cloud service providers who are managing all the other aspects of it may be seen as sufficient. So if I'm using Android Auto and my vehicle is reporting information through Android Auto to Google, who then is doing live updates of maps for people who are driving around, that is kind of replacing some of the functionality that people thought V2V or V2I was going to implement. Because what it is intended to be, at least in theory, is that if you have this network of cars and they all have this smart device functionality, they can actually then communicate with each other. So my car is communicating with other cars. My car is communicating with upcoming street lights or stoplights, excuse me, saying, hey, car is coming, perhaps adjust your stoplight algorithm because there is actually a car coming. Vehicle to pedestrians, it was also seen as being, we have a wheelchair or something of that factor, something of that nature, or bicycles, and hey, watch out, there's this oncoming vehicle traffic and vice versa, there's pedestrian traffic, and adjust speed and things of that nature. There was a very big vision for that as being the future of intelligent transportation systems. It may still come to pass. It doesn't seem to be proceeding, at least in the US, at a really rapid pace beyond just vehicle to device. Some Ford vehicles do have V2V and V2I capabilities. I kind of looked that up. I own a Ford vehicle that's relatively modern, and it looks like it's primarily in China, where they can actually signal the stoplights and say, you know, car is coming, turn to green if there's no other cars also coming. For the most part, it's not in proper use. But as we know, cars themselves, and this class isn't a class on automotive security. Cars themselves are also many, many different networks, right? So there's this physical network in your car, at least traditionally referred to as sort of a CAN bus, automotive network, controller automated network for your cars. And it is not so dissimilar from like a TCP/IP network, a little bit more simplistic than that. And that's where all the different sensors and your actuators in your cars are receiving and sending data. And then you also have wireless networks in your car as well, beyond just Wi-Fi and Bluetooth and things like that. My car is pretty new. I received this warning a few months ago, and it said low, dangerously low tire pressure in my left rear tire. And that's actually a wireless sensor in that tire that has actually a separate TPMS, tire pressure monitoring system, sends that to a controller node in your car that then displays that information back to you as the driver or user of the car. And I thought to myself, well, oh, those poor Ford mechanics, they don't know what they're doing. When I got my car serviced, a week ago, and they rotated the tires, they didn't realize there was this complicated tire pressure monitoring system in it, and they probably screwed up something with the sensor calibration. And so I took it to the dealer, kind of chuckling to myself, oh, these poor Ford mechanics. I take it in, and they mention, no, you actually drove over a nail, and that's why your tire pressure is low. But there's a lot of complex sensing and actuating happening already with a car. This is kind of something in addition to what has already been in place. And there's pretty clear security implications of that already, not to mention what could be done if you have broader V2I and V2V networks here. It has, for, I guess I would say, a solid decade been recognized that modern automobiles are eminently hackable. The term you may hear, it's kind of a weird portmanteau of infotainment system. Maybe it's only security researchers who refer to that term, but a combination of information and entertainment system, this fundamental mixing of two significantly different systems in your car, all presented to you, at least in most modern cars, is just a single screen, right? You might have a few different sensors and screens, but for the most part, you get a big tablet in the front of your car that you purchase these days. Um, and it's combining two totally different pieces of functionality. One is, can I get Spotify in my car? Can I bring up a nice map? Can I do just entertainment things? Some cars can play Netflix and things like that. Separately, can I get the sort of traditional feedback information from the various sensors in the car that in the past would have been like a blinking warning light or check oil now type of light? That's all combined by design in modern automobiles. And when you add on top of that this sort of capital I, Internet of Things functionality, where there is capability for this OnStar system, where Chevy GM can contact your car, can reach out if it thinks you have an accident, can actually take control of your car if absolutely necessary. That's a pretty big attack surface that wasn't previously there. That in older times, you still had a CAN bus, but it was a physically separate thing from any like smart device you may have had in the car. And kind of by design now, they're sort of merged networks. There's some attempts to firewall. People are aware of this issue, but fundamentally now, you have your Netflix slash Spotify slash whatever, your entertainment running in the same system as what is monitoring, potentially controlling the ECUs, the controller units that are driving your car, checking the status of your brakes, checking your tire pressure, and things like that as well. And it's all kind of combined in one system. And the concern, and in truth, the reality, is that a vulnerability then in sort of the entertainment side of things, OnStar is not exactly entertainment, but it's related to that, could then lead to vulnerabilities and exploits in the informational and the actual automotive side of things. So when you read these articles about researchers took over such and such car, it's very real. It's very possible. Someone who wants to do you harm can do you harm in all sorts of ways. So it's not necessarily something to freak out about while driving down the road, but it's very feasible. And it's understood to be a significant issue, and it's not necessarily a solved problem as of today. That if there is a vulnerability, and we talk about web application security and how modern software is just combining of so many different frameworks and libraries and gluing them together, and the provenance of all that software is not always something that we really know and have confidence in, that same issue then becomes the case here, that we wind up relying on software because we're building something that's not seen as safety critical because it's just displaying a map or something along those lines, and then it's merged, it's combined with resulting safety critical systems in your vehicle, and that's why these kind of exploits do happen. That's sort of a DARPA challenge to show that cars could be taken over. This was a pretty well-publicized incident. Miller and Valsek showed how they could take over a Jeep Cherokee. I linked the article to that, and just a write-up of their Black Hat 2015 talk. And the picture's kind of silly here, but they showed that there was kind of default Wi-Fi security passwords on those Jeeps. They weren't all hard-coded, but there was a very straightforward algorithm, just like our quiz code algorithms, that one could reverse engineer to determine for a given car what its Wi-Fi default password would be. And they were able to show that once you had access to external Wi-Fi connectivity to a car, you could then access this automotive network. This CAN bus is part of your car. And that's a whole separate kind of skill set, understanding those signals and what those CAN bus looks like and how it controls things. We don't teach too much of that in our department, electrical and computer engineering. Agricultural and biosystems engineering has a couple of CAN network courses for farm and industrial type equipment, but it's very similar to what's in commercial cars, consumer cars as well. And it does turn out that once in this vehicle, once you had access to it, you could overwrite signals on the CAN bus. And it's probably quite challenging to use those signals to take sort of full control of a car. But just like with software, it's usually a lot easier just to crash something than to actually do something malicious and intentional. And that's what they were able to show, that you write enough garbage on the CAN bus, you can mess with the brakes, mess with the ignition, do all sorts of things, and in this case, forcing a recall of many, many cars. That's a long time ago. You may think that's not an issue anymore, but much more recently, it was shown that effectively all Teslas were remotely hackable. And possibly by design. Um, whether the implications that were fully understood at the time. Teslas were kind of at one point very innovative in terms of the infotainment system and what kind of software they were providing. They weren't relying on either CarPlay or Android Auto ecosystems. They kind of build their own third version of all of those things. And this is a pretty interesting article. We won't go through all of it now. Um, Looking at what the Tesla infotainment capabilities provided, this is just some 19-year-old. I don't know if it matters that the person's 19-year-old, so roughly your age, hacker. And they were looking at this device connected on their network, and we won't go into all the details. What tool did they run there to generate that first screenshot? Nmap, right? Okay, so at least should look roughly familiar here. Um, What does it tell you about what's running on that car, at least as remotely accessible, just by looking at that screenshot? A couple things. I don't know if you can read it. Sure. Actually, I don't know if I can. Well, let's try. There we go. A very light Nmap scan. We talked about light. First two things. Let's not worry about the last two. What's it running on there? It's running a web server of some sort, at the very least, right? It shows here running free civ, open source civilization. That's probably not what it's running, right? When Nmap finds an open port, it also has a database of sort of known ports that people use. But once you get past a certain number, I actually don't remember what the exact number is. Nothing's really reserved anymore, and this just happened to be what was in a database. I'm almost certain the car was not running free civ. What do you do next? You have open ports, you try to connect to them. This guy tried to telnet, that didn't work. Recognize that, well, if I actually open a web browser and open up to that particular port, not the 80 or 443, but I think the 5555 port, there is this well-known kind of Tesla management software running called TeslaMate, and it just turns out that plugging around with it can find things like vehicle driving history, as well as effectively free access to all of the basic Tesla automation that is available to more authorized, authenticated users of the car. Not full takeover, at least to my knowledge. You can't remote control drive a Tesla. You can tell it to come to you. You can turn it on. You can turn it off. You can roll down the windows. You can unlock the doors. You can do all sorts of things that through the app effectively. And that turned out to be pretty much entirely open, uh, sort of by design, or sort of with the understanding that, well, we have this one point of authentication that someone has to be within sort of Wi-Fi range of it to be able to access it. Something of a physical security perimeter that probably doesn't make sense in the context of cars that by nature have to drive all over the place. People can be near your car while it's on to determine what it is trying to do. That's not to say our cars are all entirely insecure. Automotive manufacturers are aware of these issues. Um, they're also in the business of making cars, right? They're not in the computer security business. But if you want to look for internship opportunities that are maybe less explored, whether it would be the Ford itself, but more likely to be a Ford, like a third-party provider for them or a contracted manufacturer for them, there should be lots of opportunity to understand the security posture of the resulting software running in those cars. Or go work for Tesla. They hire plenty of our students as well. I want to talk briefly about smart grids. This is a whole separate course we do offer in this department on smart grid security. When you're a senior, you may want to consider taking that one if you've kind of made your way through all the other kind of core required courses. There is all sorts of reasons and benefits for why people have wanted to deploy a smarter grid infrastructure. There's kind of a bi-directional reason, but the other term you'll see is advanced metering infrastructure. The idea being that if you provide network mechanisms, at least at sort of the end user node, so at your meter itself at your house, that should allow sort of the network as a whole, as well as you as an individual customer, to use energy more efficiently. It's as simple as saying, we are going to plug in your electric car and use it. But if everybody is plugging in their car roughly at 6 p.m., and that's roughly when people are getting back from work, we can actually use the electric grid much more efficiently, perhaps save people money as well by broadcasting that information and using it to kind of schedule energy usage more efficiently. People generally, when they plug in their car, they need it plugged in. They don't necessarily need it plugged in and running instantly that minute. They need the car charged by the following day or a few hours later. Or things like your washer dryer system, if it's electric, you do need the washer to run. You may not care if it runs at 6 o'clock versus 6:01 versus 6:02, and those kind of global decisions can then get made based on the load, based on the demand, should lead to savings for someone at some point along the line with a more intelligent management of the whole demand of the system. But as that has been rolled out, it has been, equally recognized that, again, as you add smart to a term, as you add IoT style technology, you have then also created potential vulnerabilities. Again, the cybersecurity vulnerabilities are well understood. It's a network interface, has open ports, people can start to explore and see what things can happen, right? But then what happens on the physical side is what makes it more interesting, right? On the physical side, your car drives off into a ditch. That is a little bit different than your laptop, getting rooted. And the cyber physical smart grid here, well, you can imagine all sorts of things that can happen, right? Things like blackouts are not a theoretical concern with the smart grid. The pushback on these kind of proof of concepts as well, this smart grid wasn't very smart, and that's why these things can happen. It's possible that as people put in more advanced networking functionality, that they'll learn some of the lessons that have been learned, via the cybersecurity community. This is the Aurora generator test. That is a diesel generator, the kind of thing you probably don't encounter in your day-to-day life, but they are critical to keeping the lights on across the country. That was networkly accessible, and this was intentionally shown, that, and there's a little bit of nuance of how they did it that I didn't entirely understand, that it wasn't just turning it on and turning it off, but if you were turning it on and turning it off with a certain cadence to it, that winds up messing up the underlying physical hardware and, can cause some serious catastrophic failure here. Let's actually play the video, though, while we do that. I included this here because it looked kind of cool. That's the main reason. So we talk about smart car. You can kind of visualize, okay, if someone's able to take over your car, that is a problem. Smart grid, and this is one component of what would be a smart grid. This is a pretty large-scale diesel generator, the kind of thing that helps the lights in your community stay on here. And if it did have effectively a smart light bulb attached to it, right, like a networked on-off switch, for want of a better simplification of what's happening here, well, you can only do so much damage to a light switch, right, or to a light bulb, on, off, on, off. Turns out, given the somewhat advanced electrical control mechanisms happening here, that toggling that effective light switch on and off led to black smoke, which we know is really bad with our electronics. Apparently, it's very bad with our diesel electronics as well here. So it blew up, long story short. That is one particular piece of hardware, right? But that is a critical component of the grid, right, of our electrical grid, the power generation side. And there has been both kind of theoretical exercises and somewhat declassified real-world examples for which the grid of warring states was specifically targeted. Now, these things can be targeted via bombs as well, right? So it's a new vector. It's not a new concern in warfare that people would want to destroy, fundamental infrastructure here. But it was believed, this is from a 2015 example, and supposedly it's been hardened since then, that as part of that initial concerns between Ukraine and Russia and over Crimea and things like that, that there were attacks on the Ukrainian grid, that cyber attacks on the Ukrainian grid. In terms of what that would look like, none of that is really truly publicly known. But once you have computers, once you have network ability to monitor and to control, once you have the IoT, once you have the on-off switch or the smart bulb, then things like this on various scales are possible. You don't have to have them blow up for the grid to be taken offline here. And there's belief that the U.S. grid is also considered vulnerable as well. This article, I have it here. I don't recall what source it was published in. um, some utility journal here. It's not that clear. The headline is obviously pretty serious here. This was on the control room side, where again, if you have some network vulnerability, then people can get remote access and do all sorts of bad things here. It's not clear if they had sufficient access to shut down parts of the grid. I could not find an example that was pretty clearly laid out that, yes, it was hackers who took down part of the United States power grid. It could have happened, and that's the kind of thing you wouldn't hear about in public for N number of years afterwards. But it's certainly possible. There's no reason to believe it's not something that's feasible. It's just a matter of the degree of difficulty of such an attack in doing that. So again, this is just more flavor as to why when we talk about IoT security, people wouldn't normally refer to this as IoT, but it's the same general concept, right? Where you have a physical device, something physical that previously was quote unquote dumb, right? That previously was just doing its job, required effectively manual intervention to change some setting, to turn it on, to turn it off. And for good reason, there was desire to add the smart functionality to it. Now you have a lot of these devices that is now both the physical device as originally intended and a pretty mediocre PC connected to it, right? That's what we basically have in these devices. And while we have gained in the more general purpose security community a pretty hard fought understanding of the kind of weaknesses we have to watch out for, the kind of vulnerabilities we have to check, we're having to essentially relearn some of those lessons because it's not the same people. It's not the same players in the game who are deploying smart grid, who are deploying, workstation operating systems and servers and things like that. It's different people with different expertise, different skill sets, leading to kind of having to relearn some of the same results. This is a little harsh, but this conclusion is that IoT security results from a design, development, and support philosophy that focuses on cost and other criteria before security. I described that prior to this as being sort of just economic or financial pressures on these particular devices. If your smart light bulb is selling for $3.50 and it won't sell at all if it's priced at $4, that has certain implications of the resulting cybersecurity of the device. There's just an economic argument for that. The result tends to be just very fragile solutions. And then when you add on top of it that IoT devices, at least not as frequently, are less visible and the consequently part less of a comprehensive security policy, that leads to these kind of potential issues. It's something that I know Iowa State is very concerned about. You bring your smart light bulb, and I know for a fact, unless you have connections, it's very hard to get that smart light bulb on the Iowa State network to be able to control it remotely. So be it. That's a smart trade-off, perhaps, that Iowa State is making. But if it's your home network, you get to control what things are added and not added there. It's a very tricky problem to solve. How do we secure, the 37,000 computers we already have on campus, or whatever that final number winds up looking like, plus then perhaps 4 to 5 times that many smart devices that we can't have a single policy for unless we're being entirely restrictive on them. And the last thing we'll talk about is just 2 illustrative examples. The fish tank's not that interesting, but the Ripple 20 was a well-publicized set of vulnerabilities. I tried to understand why it was called Ripple 20, to be honest. It's not that important. My first thought was, well, they found 20 vulnerabilities. No, it turns out they found 19. So my next question was, why isn't it called Ripple 19? Perhaps they had 20 and then one of them wasn't a vulnerability. The other thing they claim is that many of these vulnerabilities had been in place for over 20 years. That could be a reason to call it 20. I don't actually know the answer. It's just what it is. It was a well-publicized set of vulnerabilities in an extremely popular TCP IP stack. Now, you may ask, right? What does it mean to have a TCP IP stack? We know it's a piece of software. We normally don't concern ourselves with the security of a TCP IP stack. Why is that? Well, because there was hard-fought battles in the 1990s to really audit these things and ensure that the people who wrote them, Microsoft, Linux kernel developers, thought very clearly through some of the security implications of it and continue to audit and improve and make that code more robust. That is for traditional computing. IoT computing, in which you're not necessarily running a full-blown kernel, you're certainly not going to be running Windows on any of these devices, is going to still need networking capability. Oftentimes, it's going to be running in user space, but it's going to be using some other third-party, presumably open source software stack to do the networking on that device. This is one of many. It's referred to as the TREC, is the name of the company, TCP/IP stack. There is nothing wrong with it other than it was written by an engineer 20 plus years ago and then never looked at ever again. Checked off, this is a solved problem. It was available at a relatively low cost. It became something of a default choice for all sorts of different devices to use for their networking stack. Again, if you purchase a new laptop, this is not something you have to worry about. You're going to install an operating system on it, presumably, and there's a level of trust involved that the people you are purchasing or downloading the operating system from have worked through these issues and have a relatively well-implemented stack here. This one was not the case. There wasn't any independent audits of it until this point of time. And for these IoT-style devices, there turns out to have been a number of different pretty red flag vulnerabilities. When you see a CVSS score, as we've talked about, of 10, that's not good, right? That's a sign that things are really bad for the security posture of that particular device. The actual exploits are a little subtle. I always like to provide examples of exploit code here, and there's a few links I provided for that. There is a very nice white paper of what it does. I think it's probably a bit too technical for us, but we can take a brief look at what an example exploit is. This one is not intended to do anything too severe, so this is using just a very well-known sort of low user-level networking Python library to kind of create packets. And it's basically showing a buffer overflow exploit. It's a little subtle because it's not really doing anything that interesting in and of itself. Sending an IP packet, UDP, and it's just sending a bunch of bytes over. And it turns out that if it's connected to a device that was running that version of the TREC TCP/IP stack, this would cause that device, that user process, to kind of crash out. And then on top of that, now it has to be probably device specific what the exploit would be doing, that if you then more carefully craft the particular payload that you're sending over that UDP IP connection, it's in here somewhere, you can have it to do all sorts of things. The reason we can't go too much into this, we talked about this a little bit previously in the semester, that when looking at malware, the couple things that you will find are, for example, what this one's referred to as shell code. Shell code, at least historically, used to refer to what is the bare minimum number of instructions that would allow me to get a reverse shell on the machine, and we play around a little bit with that ourselves. This is not getting a shell. This is ARM assembly instructions to blink some LEDs on a particular device. So it's the exploit proof of concept. It's not actually reverse shell. The reason the code becomes very hard to actually analyze is it's doing something we talked about briefly called return-oriented programming, where there's a set of instructions it needs to run, but it can't actually overwrite the instruction memory, so it has to find the equivalent ones and zeros of those instructions elsewhere in the memory space, and in doing so, it kind of hops all over around data memory to be able to get those values. We don't necessarily need to become, experts in terms of what's happening with all these vulnerabilities, but as an illustrative example, TCP/IP network stack, fatal, remotely accessible vulnerability is not the kind of thing you would see in Linux, for 25 plus years. IoT device, for various reasons, cannot just take the latest greatest version of Linux and just slap it on the device. Using a lower powered device, using a device that may not be directly supported for various reasons, might be missing some hardware capability, could just be aspects of lack of expertise on the manufacturer side, lack of resources to properly deploy and test. And the end result is you have presumably what is seen as a category 10 vulnerability that was in place, whether it was known or not, for nearly 20 years here. That is what makes IoT security a little bit more important than or separate from traditional network security. Yes, there have been TCP/IP vulnerabilities in more traditional network stacks over time, but this IoT community is having to sort of relearn some of the lessons that we had to learn through that era and that period of time. It's not so simple as saying let's just take the code that we know is decent and apply to these devices. These devices can't necessarily even run that code. Um, I want to talk about botnets, but let's do it next week on Tuesday. Otherwise, good luck finishing up the current lab, getting started on the next one, and I'll see everyone on Tuesday.